Welcome back to the AI Research Roundup. I'm your host, Alex. Today we're looking at BLIP3-o, a family of fully open unified multimodal models architecture, training and dataset, from May 14th, 2025. This paper introduces BLIP3-o, a new set of unified multimodal models, which are AI systems designed to both understand images and generate new ones. A key idea is their use of a diffusion transformer, a specialized model architecture to create very detailed clip image features. These clip image features are rich numerical descriptions of image content, improving both training speed and image quality. They also curated a new instruction tuning dataset, which helps these models better follow diverse commands for image generation. And for those of you who want to get hands-on, well, the authors have also released the BLIP3-o GitHub repository. It's got all the code for this work, including things like modeled checkpoints, which are essentially saved versions of the trained model, along with training recipes and inference scripts, so you can really dig into how it understands and generates images. Alright, so this figure 1, lays out the architecture of BLIP3-o, showing how it handles both image understanding and image generation. It's a really nice visual of how these two capabilities are unified. You can see two main pathways. On the left, for image understanding, an image, let's say of a corgi, is processed by CLIP to get those rich clip image features we talked about. Then, an autoregressive model, which is a model that predicts step by step, uses this information to generate text tokens, guided by a mathematical measure called cross-entropy. Cross-entropy, here, helps ensure the generated text accurately describes the image. Then, on the right, for generation, the process starts with text. This text is converted into a text embedding, which is basically a numerical summary of the text's meaning. This text embedding, along with the autoregressive model producing an intermediate visual feature, feeds into the diffusion transformer. This diffusion transformer then uses a technique called flow matching, which is a sophisticated way to guide the generation process to transform initial random data, or Gaussian noise, into detailed clip image features, ultimately creating a new image. The shared autoregressive model and the use of CLIP on both sides are key to how BLIP3-o unifies these tasks. Okay, so building on that architecture we just discussed, Figure 2 now shows us some of the actual images generated by the BIP308B model. And these are high-resolution images, 1024x 1024 pixels. What's really striking here is the diversity of the content it can produce. From realistic portraits and animals to more fantastical scenes, and even images with text embedded in them. It really gives you a sense of the practical output of that image generation pathway we saw in the diagram. Alright, so following those impressive generated images we just saw, Figure 3 now digs a bit deeper into the design choices specifically for the image generation component within this unified framework. It lays out 3 different approaches they considered. All these designs start with a text prompt and use that autoregressive model we discussed to produce an initial visual feature. Where they vary is in how this visual feature is then transformed into the final image. Option A uses clip image features and an objective called mean squared error, or MSE. MSE is a common way to measure the difference between what the model predicts and the actual target. Option B, which is the one BLIP3-o ultimately uses, also starts with clip image features but pairs them with that flow matching technique using a diffusion transformer. Then, option C explores using A, variational autoencoder, or VAE, which is a type of neural network that learns to efficiently compress and then reconstruct images, also combined with flow matching. An interesting note is that when using flow matching, they keep the autoregressive model's parameters fixed to preserve its language understanding abilities while training the image generation parts. Okay, so we just looked at the conceptual design choices for image generation. Now, Figure 4 gives us some quantitative results, actually comparing how these different approaches perform over training steps. We're seeing 3 key metrics here. First, there's the Gen-Eval score and the DPG score, and for both of these, a higher score is better, indicating better image generation quality or alignment. Then we have the FID score. FID stands for Frechet Inception Distance, and this metric measures how similar the generated images are to real images, so a lower FID score is what we're looking for. Across all these plots, the red line, representing clip image features combined with flow matching, which is the approach BLIP3-o uses, consistently shows strong performance. It generally achieves the highest General and DPG scores, and the lowest, meaning best, fit scores as training progresses. The blue line, clip with mean squared error, is competitive, but the green line, using that variational autoencoder with flow matching, tends to lag behind, especially on General and DPG score. This data really backs up their decision to go with clip features and flow matching. So, after seeing how the design choices panned out in Figure 4, Table 2 here gives us a broader look at how BLIP3-o stacks up against other models on standard image generation benchmarks. We're again looking at Geneval and DPG bench scores, where higher is better, and there's also the WISE score. WISE, or Wasserstein Inception Score with embeddings, is another metric where higher scores indicate better image quality and diversity. The BLIP3-o8B model, using that preferred clip and flow matching approach, achieves an excellent Geneval score of 0.84 and the top WISE score at 0.62, which is quite impressive. So BLIP3-o really demonstrates strong performance across these benchmarks, especially with that clip and flow matching combination. The key takeaway here is that we have a new family of fully open multimodal models that are not only powerful, but also efficiently trainable, which is a big deal for making advanced AI more accessible. This work really pushes forward the open-source multimodal landscape. Well, that's all the time we have for today's AI Research Roundup. Thanks for tuning in, and I'm Alex, signing off.